Okay, this section's on counting techniques. The objectives here are to solve counting problems using the multiplication rule, which will also be known as the fundamental counting rule. Okay, and then we're going to discuss permutations and combinations and what those mean. Okay, so let's start off with a very simplistic example to illustrate this first concept of the multiplication rule. All right, so let's read this. It says, example 1. If there are 3 different color paint, red, blue, green, that can be used to paint 2 different types of toy cars, then how many different pairs of toy cars can there be? Hint, draw a table with all the possibilities. Okay, so we have car 1, car 2. So let's just assume that we can actually make the distinction. Maybe one's a car, one's a truck. And we're going to paint them either red, blue, or green. All right, so if we paint the first car red, we can also paint the second car red. There was no restrictions. There's nothing that told us that we couldn't do that. And then red with blue, and then red with green, right? Okay, so we've already exhausted the red with all the other combinations of colors for the car 2. So we go on to blue with red, blue with blue, blue with green, and then finally green with red, green with blue, green with green. So if we count those up, we get 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 9. Now that wasn't too hard to do, right? We've pretty much figured out we can, all the different ways that you can color these 2 cars using red and blue and green paints, right? And that wasn't too hard to do, right? But what I can very easily change this to make it a little bit harder. Like if I had like 4 cars and maybe 5 different colors of paint. You see how that would take some time. So there's got to be some sort of shortcut to do this, right? To kind of figure out that count of 9, okay? And that is this multiplication rule, okay? So it says, in order to come up with the total possible outcomes in a series of decisions, it's found by multiplying the number of choices by each category as follows. So we're going to make a slot for each decision. So how many decisions were we making in the previous example? Well, I would say there's 2, because we're deciding on what to color car 1 and what to color car 2. So we're going to make 2 slots here. Car 1, car 2. Okay. Enter the number of choices for each decision in each slot. Okay. Well, for car 1 we had how many choices? Well, 3, red, blue, or green, right? And then for car 2 we also had 3 choices. And then we just simply multiply these numbers and we get 9, which was exactly the same count as we got before. Okay. So here's another example that illustrates this. So for example, if I were to give you a quiz, a very short quiz, a 2-question quiz, and the first question was a true or false response, and the other question was a choice of 5, right? So you can either, if you were to answer true for the first question, you can go true, and then A, B, C, D, or E, so you have a T, A, T, B, and so forth, and then the same for false, right? So you can see that there were 2 choices for the first question, right? And there's 5 choices for the second question. So you're making 2 decisions, right? And so if you just do 2 times 5, you get 10, which is exactly what you would get. All the different possible responses that I would probably get back from those quizzes. Okay, so let's continue. It says example 2. A child is coloring a picture of a shirt and pants. Okay. If there are 5 different color of markers, then how many ways can the shirt and pants be colored? Okay. All right, we always have to ask ourselves, how many decisions are being made? Okay, well, we're deciding on what to color the shirt, and what the color of the pants. So let's go ahead and make 2 slots for each decision, or a slot per decision. And what did they say? How many choices do we have for each one? Well, they said we have 5 different colors of markers, and there wasn't any restrictions on you can't color the pants and shirts the same color. So we have 5 here and 5 here. Therefore, we have 25 different ways that these shirt pants combinations can be colored. All right, example 3. A 4-digit code is used for a keypad on the garage door opener. How many 4-number codes are possible if the number can be only used once? Ooh, so they put a little bit of restriction on us, right? Only used once. Okay, so there's a 4-digit code on a keypad for a garage door opener. All right, so, well, how many decisions are you making when trying to come up with the correct code? Well, it should be 4 digits, right? Because you're deciding on what to enter in first, then second, then third, then fourth, right? So there's 4 decisions. What to push first, what to push second, what to push third, what to push fourth. Now, well, assuming that by digits they mean 0 through 9. Well, 0 through 9 is 10 choices for the first choice, for the first decision, right? Now, you can't use the same number once. So you no longer have a pool of 10 choices for the second one. You have what? Well, 9. Well, you've already used up 2 numbers, so you have now 8 for the third choice. And then you have 7 for the last decision here. Okay, and if you just multiply those out, what do we get? Well, 10 times 9 times 8 times. I get 5,040 different ways. And the follow-up question here is, what is the probability of guessing the code correctly? Well, there's only one correct code out of how many possible? Well, 5,040. So 1 out of 5,040. Now, there's one thing to kind of note here. That little restriction there of using only the number once, you might say, well, is that for security purposes? Does that mean that it increases the number of possible ways? Well, let's think about it. If we didn't have that restriction, and you could still use the numbers the same amount of times, like you can use a number more than once, well, we would have, for the first choice, 10. Second choice, you would still have 10, right? There's no restrictions there. 10 times 10 times 10. There would actually be 10,000 different ways that you can put in the code, right? And then the probability would be 1 in 10,000, which is a smaller chance. So this whole restriction here doesn't necessarily make it more secure in terms of there's more possibilities. What it does is it helps avoid people just putting in those common passwords like 555 and so forth. Okay, so moving on. Okay. All right, so let's discuss this factorial symbol. Factorial symbol. N factorial. Well, that little exclamation mark, it's read as factorial. Okay, so n factorial. So what that means is n factorial equals n times 1 minus n. I'm sorry, n minus 1 times n minus 2, all the way down to where you get to 1. Okay. These are what are known as permutations. Okay, so just as an example down here, how is this actually used? Well, if you're just using 5 factorial, it's just going to be 5 times 4 times 3 times 2 times 1. If you multiply all those out, you get 120. Okay, well, you might be wondering why are we even talking about this? Well, if in the previous problem, we did notice that it went from 10 to 9 to 8 to 7, right? So it seems like we're going to be dealing with problems that you're not going to be able to use the same number again. So let's see that. Example 4. If I need to run errands to 6 different places, how many different routes are possible? Well, if we have to run errands, you typically don't have to go to the same place twice, right? And if you have to go to 6 places, well, we're making 6 decisions, right? Where to go first, where to go second, where to go third, where to go fourth, fifth, and sixth, right? You have 6 places to go to. On your first choice, or on your first decision, you have 6 choices, right? Once you've gone to one place, you no longer have to go there anymore, right? So you're now down to 5 choices for the next decision. And then you keep knocking one down. And on the last decision, there isn't really any choice. It's just one choice, right? And again, this would just be 6 factorial. Okay, so 6 times 5 times 4 times 3 times 2 times 1 is equal to 720. Okay. All right. Solving counting problems using permutations. Now, the factorial rule was used to count all the different arrangements of all n items when all n items were selected. Okay. So in the previous problem, there were 6 places to go to, and we needed to go to all 6. Okay. But what if we only had time to go to like 3 places, right? So some you're going to choose to go to, and some are going to be excluded. So that's what this is all about. Okay. So a permutation with the denoted permutations of n choose r, n decisions r choices, is an n choices n decisions is an ordered arrangement in which r different objects are chosen out of n different objects, and repetition is not allowed. The formula is given by this. Now this formula looks kind of ugly, right? It has a bunch of factorials and a bunch of letters, and this is all probably brand new to you, okay? But it really is just the fundamental counting rule, and I'll show you that in an example, okay? Again, there are essentially 9 n objects that are distinct, okay? Essentially, you can think of this n choices. A repetition of objects is not allowed. So it's like in the previous problem, you can't go to the same place twice. Now in this case, order actually matters. Order matters. Okay. And there's certain things in the problem that will indicate whether order matters or not. Okay. And they're kind of subtle in some in most cases. All right. Example 5. In how many ways can Example 5. In how many ways can people in a 1,000-person marathon finish first, second, and third? Okay. All right. So let's think about this. There's 1,000 people to choose from, right? And there are 3 essentially assignments: first, second, or third, right? You can think of these as decisions, really. Who to crown as first, as second, and as third. Okay, so let's go ahead and do that. Now I kind of want to split this down the middle and show you 2 different methods. And let's start with the fundamental counting rule. Fundamental Okay. So we have essentially 3 choices. Who's going to be first place, second place, third place. All right. And there's 1,000 people in this marathon. Well, if you have 1,002 people that can possibly be first place, then there's 1,000 choices, right? Now, first place person can't also be second place, right? So we no longer have 1,000 people to choose from to figure out who second place is. We have 999. And then same thing with third. First and second have already been assigned, and third would be 998. And that is actually your answer here. Okay, 1,000 times 999 times 998 equals, oh, big number, 997 million 2000. There's that many different, what we call permutations of first, second, and third. Okay. And why does order matter? Well, because if you have, let's say, Bob, Mary, and Sally, that would be a different permutation than Sally, Bob, and Mary, right? Because they're in different places. Okay, they're just different permutations, different arrangements. Okay, if we're just using the formula, well, we have to figure out what your n is and what your r is. Okay, r is the number of decisions that are being made. Okay, in this case, there are 3. And then n is the number of choices that we have. Well, we have 1,000, and out of those 1,000, we're going to choose 3. Okay. So it's going to be NPR is actually going to be 1,000 permutations of 1,000. Choose 3. Okay. Let's actually use this formula here. So 1,000 P3. Well, if we follow this formula, n is 1,000. So we have 1,000 factorial. And then we have we have 1,000 minus 3 factorial, right? Because that's your n, that's your r. All right, now you can't apply this factorial rule until we have a single number here. So we first have to subtract those out. So you have 1,000 factorial in the numerator. Denominator, we have 997 factorial. Okay. Now, and you'll probably see what we're going to end up having. Now this 1,000 here, I'm going to go ahead and start expanding it. Okay, that'll be 1,000, 999, 998, 997, and so forth. All right. Now it doesn't look like we have a lot of room, and in some cases you won't have a lot of room, but let's just see what happens. We have 1,000 times 999 times 998 times 997, running out of room. But in this case, we actually want to stop here because 997 and everything else to the right of it, that's the same thing as 997 factorial, right? Because that contains everything that's less than that, right? And what do we see downstairs in the denominator? 997 factorial. Now, all the same factors in the numerator, 997 factorial, all those factors that are contained in that quantity are the same that we have in the denominator. So those can actually cancel out. And what are we left with? Well, we're left with the exact same thing that we had from the fundamental accounting rule. 1,000 times 999 times 998. Okay, which comes out to be 997,002,000. Okay, now, well, which way was easier? Well, it depends, right? It depends. This particular problem was easier if you just used the fundamental accounting rule, right? Because there was only 3 choices, right? 3 decisions being made, right? But what if we were interested in the first 10 or first 25? It would actually have the right 25 little slots, right? Because you need a slot for each decision. So it can kind of get tedious. And if you have a formula for something like this, well, this can also be pretty tedious too if you were to do it by hand. But the nice thing about a formula is that you can get a calculator to do this for you. Okay, so let me show you how to do that on the calculator. So if you turn on your calculator, just make sure that your screen is nice and cleared out. And the way you want to input this in is you want to put it in just the way you see it, 1000 P3. So let's start with 1000 on the home screen. Okay, in order to find this function, this permutation function, we're going to have to push math, which is 3 rows from the top, and then go all the way to probability, PRB. And you see there's NPR, there's also that factorial symbol, there's also NCR, which we're going to talk about soon, NPR. And then what it wants now is the R. In our case, the R was a 3. Okay. And if you just press enter, then you get that number. Now, factorials can actually account for all the different arrangements that we can make from a certain amount of decisions and choices. So let's start with a simple example. Okay, say we have an A, a B, and a C. Okay, we want to see how many ways these can be arranged. Okay, so let's start with, well, what we see there is A, B, C, and then this one going to be A, C, B, right? And now that was A first, right? Now we can't rearrange these anymore, so now we can go on to B, B, A, C, and then B, C, A, and then we can go to C, A, B, and then C, B, A. So these are all the different arrangements of 3, okay? And what you notice here is for that first choice, how many choices do we have? Well, we had 3, right? Once we made that first choice, then how many choices do we have? Well, we had 2 essentially. And then finally we just had 1 left over. This is just 3 factorial. Okay, I'll illustrate this again with just 4. Let's say we had an A, B, C. A, B, C, and D, I mean. Okay, so I'm saying that for the first one we have 4 choices. Second one we have 3 choices, right? Because you can't use the same letter twice. And then 2, and then 1. Okay, this is supposed to be 4 factorial. This one came out to be 6. What would this be? 4 times 6, 3 times 2 would be 24. Okay, let's see if we get that. All right, so we have A, B, C, D, A, B, D, C. So I'm just going to rearrange those. A, now I can start with C, B, D, A, C, D, B, and then A, D, B, C, A, D, C, B. Okay. So for A, there were 6 different ways you can do that. And if we did that for B, you can kind of get an idea. We have 6 here. If we do it for B also, B, A, C, D, B, A, D, C, B, let's go with C, A, D, B, C, D, A, and then we go B, D, A, C, B, D, C, A. Okay, and then we have another 6. Now if we did that also for D, A, B, C, you'll have another 6 here. I'm sorry. Yeah. Or actually, if I want to go in order, I can do C, A, B, D, and then there's going to be 6 ways to have C first, and then you can also do D, A, B, C, and there's going to be 6 ways to have. So 6 plus 6 plus 6 plus 6 gives you 24. Okay. Okay, moving on to combinations. Okay, so combinations are very similar to permutations. The only difference here is that order does not matter. Okay, and in the formula, it looks very similar to permutations, except for there's an additional r factorial there. Okay, now if order doesn't matter, then that means we need to essentially remove different arrangements that are repeated. Okay, and that's what that r factorial essentially does. Okay, so let's do this problem the same way that we did permutations. Okay, I'm going to start off with the fundamental counting rule. Now the fundamental counting rule actually comes up with the number of permutations. Okay, and permutations are where order matters. But combinations, order does not matter. So we have to use the fundamental counting rule with some sort of modification. So I'll just write this as with modification. Okay, and then I'm going to just the straight up formula on your TI calculator on the right hand side. All right, so let's read this example. It says, If there are 8 researchers and 3 of them are to be chosen to go to a meeting, then how many ways can we choose the 3 researchers? All right, so first of all, when you're dealing with these types of problems where you have a pool of choices, in this case 8 researchers, and we can only choose some of them, in this case just 3. And they're asking how many ways can these 3 be chosen? Well, we have to ask ourselves, does order matter? Okay. Well, if you're taking 3 people from the 8 researchers and putting them into a meeting, order shouldn't really matter unless they have some sort of specific role at the meeting. Like one person's presenting, or one person's presenting last, or one person's presenting second, or one person's taking notes. If they had particular orders in which they are being chosen to go to the meeting or present at the meeting or have certain roles at the meeting, then yeah, order matters. But if you're just having 3 people and they're just going to go to the meeting and apparently it looks like they all have the same role, then order does not matter. Okay. So again, how many decisions are being made? Well, we have first person to take, second person to choose, and then third person. Okay. There are 8 researchers. So we have, for the first choice, 8 to choose from. We've already chosen 1, so now we only have 7 for the second decision, and 6. So this will give you actually the number of permutations. Eight times 7 times 6 is 336. Now, in order to remove all the different replications of the same, what we call combinations, right? Like Bob, Sally, and Mary. Since order doesn't matter, this is accounting for Bob, Sally, and Mary, and also Sally, Bob, and Mary. And it's accounting for all those different orders. We don't care about all those different orders. We're just looking for all the different combinations, okay? So what we do with this number here, we want to remove repetitions, okay? So we get this 336. And from the previous example, well, how many ways can you rearrange 3 people? Well, in that previous example, it said ABC was arranged essentially 3 factorial, right? And that came out to be 6. So we can rearrange them 3 factorial. So that's how many repetitions are of each combination are included in this permutation. So we have to remove that by dividing by that, okay? 336 is 3 times 2, which is 336 is 6. Divide those 2 numbers out and we get 56 combinations. Okay. So there was 336 different permutations, but a lot of those combinations were repeated, right? Essentially 6 times. Each combination was repeated 6 times. So we divide 336 by 6 and we actually have all the different combinations, which is 56. Okay. Using the formula, again, your n would be 8. Your r in this case would be 3. And we have combinations of 8 choosing 3. Okay. If you use a calculator here, just like we did in the previous section, we will actually get, again, 56 if you're just using your TI calculator. Okay. Now here are all the different calculator functions for factorial. This is how to access that. Permutations, and then again, combinations is in the same menu as permutations. Okay, and it's done the same way. We have to type in the n first, and then go to the menu, and then type in the r, just like we did in permutations example. All right, now I kind of want to get you to understand the combinations of permutations a little bit in more depth. Okay, because you might not have gotten the gist of it from the previous examples. So I decided to come up with this example here. So understanding combinations of permutation. So let's say we're packing for an all-day trip, and we can only pack 3 out of the 4 available snacks. Okay. So I guess in your kitchen, you just have an apple, a banana, carrots, and Doritos. And your backpack for the day it's small, so you can only actually fit 3 things in there. Okay. Well, and why did I use apple, banana, carrots, and Doritos? Well, it's just because it's A, B, C, D. I couldn't find a healthy food that started with a D. Okay, so let's look at this first green row right here. Well, this is where we choose to bring an apple, banana, and carrot and leave the Doritos at home. Or we can choose apple, banana, and Doritos and leave the carrots at home. Or we can choose an apple, carrots, and Doritos and leave the banana at home. Or we leave the apple at home and then take the bananas, carrots, and Doritos, right? So essentially we have 4 combinations. We have 4 combinations here. That's the number of combinations, right? We notice that we didn't take into account the order, right? Because we were just taking 3 snacks and it didn't matter. 3 from 4. And there's 4 different ways that you can do that. However, how many different ways can you arrange them? Let's say, for example, snacks are going to be in for breakfast, lunch, and dinner. So it's an all-day trip. So for this first combination of ABC, those can be arranged in how many different ways? Well, there should be 3 factorial different arrangements. Which 3 times 2 times 1 is 6. 6 ways, right? So you can have the apple for breakfast, banana for lunch, and the carrots for dinner. Or you can have the apple for breakfast, carrots for lunch, banana for dinner. Or the banana for breakfast, apples for lunch, and carrot for dinner, and so on, right? As you can see, there's 6 different ways that can happen, okay? So for each combination, there's 6 different ways that you can arrange them. So the number of permutations is this total amount in this chart here, 4 times 6, which is 24. So the number of combinations here was 4. The number of ways that each combination can be rearranged is 6. So that means the total number of permutations is 24. Okay, so that's the relationship between combinations and permutations. So permutations is always going to be a larger number than combinations. Okay, and just to kind of give you an idea of how these 2 formulas are related, I decided to, if you solve this for the combinations, just divide by r factorial. You get number of permutations divided by r factorial, which is just that. Permutations is this formula. And then just can multiply the numerators, multiply the denominators, and you get the formula for the combinations. All right, let's do 2 more examples here. It says, a club consists of 50 people. The following leadership positions are randomly chosen in order from the club members. First, the chairman. Second, vice chairman. Third, secretary. Fourth, treasurer. How many different leadership organizations are possible? Okay, so we have 50 to choose from, and we're trying to assign 4 positions, right? So we're making 4 decisions, essentially, right? Now, let's ask ourselves, does order actually matter in this case? Well, yeah, they're given specific roles, so order matters. If order matters, then this implies that we're dealing with permutations, right? Because Bob, Sally, Mary, and Joseph is a different permutation than Sally, Joseph, Mary, and Bob, right? They're just because they have different positions. All right, again, let's do this 2 different ways. I mean, this is the formula way, which is mindless, but let's use the fundamental counting rule. Again, there's 4 different choices being made. We have the chairman, vice chairman, secretary, and the treasurer. There are 50 people to choose from, right? Now the chairman can't also be the vice chairman. Then we have 49 here, and the secretary, both, so it can't be repeated, right? 1 person per 1 role, right? So we have 48 here and then 47. If you multiply those out, 50 times 49 times 48 times 47, oh, this is a large number. Can't fit here. There is 5,527,200, right? We don't have to divide by anything because this is a number of permutations. So we want to include all the different arrangements. Okay. Again, what would be your, for NPR, what would be your N and what would be your R? Well, how many decisions are being made? Well, there are 4 decisions being made. And how many choices do we have to choose from? Well, 50. So this is essentially 50 permutations of 50, choose 4. And if you punch that into your calculator, you'll also get the same number. All right, let's do this next one. And then again, when you're dealing with these types of problems, again, when you have a certain number of choices and you're only limited to choose a few, then you have to ask yourself, does order matter in the way that we're making our decisions? How many different simple random samples of size 4 can be obtained from a population who is size 20? Okay, so we're taking a sample of 4 from a population of size 20. Now we're taking the sample, but do they mention anything about a specific order or positions that we're placing these 4? I guess it's kind of an abstract problem, just 4 items. Well, no. Order does not matter. And if order does not matter, we don't care about all the different repetitions. We want combinations. Okay, so let's again do this using the fundamental counting rule. With modification. Okay, so you started off like a permutation, and then you divide by the number of ways that we can arrange these decisions. Okay, so how many decisions are being made? Well, we're choosing 4, right? So first, second, third, fourth. All right, so we're going to come up with the permutations. For the first choice, we have 20 to choose from. The second decision, we have 19, 18, 17. Multiply that out. We have 116,280. That's the number of permutations, right? But again, we have to take this number and divide it by how many different arrangements can we do with 4 items? Well, that would be 4 factorial. Okay. Just 4 times 3 times 2 times 1 over what? 24? So divide this number by 24 and you get this many combinations. 4,845 combinations. All right. So each one of these combinations was repeated 24 times. That's why we divided it by 24, the number of permutations by 24, because we essentially overcounted each combination by 24 times. Okay. Again, let's use the calculator for this next one. Combinations of 20, and we're choosing 4. Okay. Taking out the calculator this time. And we have to type in 20 first. And then we go to Math, PRB, NCR, because we're doing combinations. Brings us back to the home screen, and then punch in 4, and then enter. And you should get the same thing. 4,845.